Okay, welcome back everybody. I think we'll just start up with the Wishart, just kind of roll through the thing that might already be obvious. This is the conjugate prior. So for inverse covariance matrix, and on the homework, those of you that came to review session, we had a pretty extensive conversation about all of this. You're familiar with the inverse Wishart because that's what's on your homework. So that's what you would recognize. I want to just point out, this is very similar to a gamma distribution. In one dimension, this would be very gamma-esque. It's actually the inverse Wishart, but it's the gamma, and the inverse Wishart, or the inverse gamma, is akin to the Wishart. So it's backwards from what you might actually think. And that's just there, just to mess with you. So, I don't know, it's just arbitrary naming conventions. What's the inverse one, what's not? So, on the homework, you would be staring at a formula like this, trying to pattern match and identify terms and everything. So the name of the game in understanding what a Wishart is understanding where the random variable is. So that's the random variable. It appears here and here. And so those are the places you would look to identify the parameters. So I'll just point out, this is a k by k, positive definite. This is also a k by k positive definite right here. That means that it's invertible if it's positive definite. So we don't even have to think if we can invert because all the eigenvalues are positive. And so that's one such condition for invertibility. And we notice that this appears in the formula inverted. So I want you to just keep in mind that's a place where you can get confused as well. And we'll see that confusion once we work through the conjugate analysis. So you're like, oh, upside down or not upside down. Bear in mind, I'm not going to ask you to do this under pressure. So on an exam, so you don't need to memorize all this stuff, but I just want you to be aware when you're doing these calculations where your potential errors might exist. That's a common place right there. Where you look for the parameters right here, this one, that always appears right here. And it's going to be next to k minus 1, where k is the dimensionality of the problem. So the same sort of thing like in a gamma where you look for the alpha minus 1 term, you just have to remember there's got to be a k in there that represents the dimensionality of the problem. So we look for it right there. And then the other thing we look for over here. So that has to do with the scaling of everything. Or that has to do with the mean of everything, where gamma I might think of as a diffusion coefficient. Now they are kind of entangled, so just remember that the expectation of E is equal to gamma omega. And so very commonly, I'll work with a parameterization like this, and I suggest this parameterization on your next homework. And what that would do is it would make the expectation of this thing omega. So that's the typical thing. That's how I like to think about it to isolate everything so I can think about the interpretation of all the parameters. I'm going to remove this and just put that back. So, and just be a little bit more general. This is the way most people write it. When I use it as a modeling tool, I like to isolate what's the mean effect and the variance, and then I can think about them a little bit more. So again, this is concentrating around some positive definite matrix, and the distribution is over matrices. So this is a space over matrices, so it's kind of a cool thing to think about. So that doesn't mean that this isn't a scalar. The density function is just a one-dimensional thing, but it involves these higher dimensional features. So this is the trace. I think you're familiar with that. Some of the eigenvalues, some of the diagonal. I like to think about some of the diagonal. But when I'm doing proofs or something like that, that's some of the eigenvalues that might be useful. We'll point out traces kind of appear in like design of experiments. Well, they'll look at these optimality conditions, and you're supposed to like maybe minimize the trace on something. So in some sense, you're minimizing some form of variability. So when you're trying to control variability, you could control the trace of something, very common technique in design of experiments, or you could maybe control the determinant. That's also some sort of a norm on the eigenspace, or the space in which that distribution lives in. So when I think about this, when I think about the product of the eigenvalues, I'm actually thinking about an elliptical space, where the sum of the eigenvalues is like a rectangular space. So maybe you can think about that a little bit. And so I would say those conditions that they use in design and experiment are pretty arbitrary, you know? And so I will point out, if you were trying to check in an MCMC format what's going to converge on this, if you had a huge matrix, you probably couldn't monitor every element in the matrix and see if it converges. So what you might do is you might monitor the trace and the determinant or something like that, and look at the trace plot for those. So trace plots of traces. So that could be a strategy that you use. I do usually say in an MCMC you need to monitor everything and make sure that it's all converged, but I realize in a high dimensional setting that's nearly impossible. So you put norms on things and you reduce, you know, what you're monitoring. But at least you make sure it converges in some sense. I always check to make sure my likelihoods have converged. So I take all my parameters, I look at their trace plots, I take those parameters, I plug them back into the likelihood function, I make sure that's converging as well, because I'm going to do inference off of that thing at the end of the day. If you were integrating something like this, V gamma minus k minus 1, e to the minus 1/2 trace omega inverse V dV. This is integration with respect to a matrix. So all that means is that you're integrating all the unique elements in that matrix. So keep in mind this is a positive definite matrix, so there's a symmetry condition sitting on everything. And so if it was a covariance, then you absolutely have this symmetry condition on everything. So just keep in mind a positive definite matrix you can factorize into a Cholesky decomposition, and you wouldn't end up integrating over the non-unique elements. So in a covariance matrix, you would only integrate over the top triangle and the diagonal, because the lower triangle has the exact same elements in it. So that's what it means when you're integrating over the space of a matrix, and this would be really hard to do, but I'm just kind of thinking about expanding this and integrating over all those terms. We kind of know from studying a gamma distribution that that has something to do with gamma functions, but you're iterating over all these different things, and that's what this is right here. So this is a multi-dimensional gamma function. It's a product of a bunch of gamma functions, and I'm not going to write down explicitly what it is, but it's a number. And that number you can forget about. It doesn't ever help you with anything. If you're coding something up in a GIP sampler, you don't actually need to know what that number is or ever compute it. So I've never actually computed this in my life. Nor do I compute that as well. But I can't forget about this right here. So this is usually the chunk that you're going to be staring at. And when you do this for a covariance matrix in a normal calculation, it's going to integrate to something proportional to this. So if I were integrating this, and I would say over my whole space of V, so this is a lot of integrals right here. I never write that down. I was just use one integral sign. So this is going to be this whole thing right here. So I'll call that star. It's just going to integrate to star. And that's how you're supposed to do it on the homework. And this is going to be proportional to omega gamma over 2. And in your problem, since it's going to be on the inverse scale, it's actually going to be raised to the minus power. That's how it's going to appear in the homework problem. I'll just point out, these have something to do with the t distribution. And that was your exercise on the homework. And we had spent at least a half hour going over this last night. So I just want to put it in video for posterity's sake. We can preserve that message. So you're looking for this thing right here. So that's what a Wishart is. And it's a cool tool if you're modeling covariances. Now you can do joint estimation of vectors and covariances and control for all that joint behavior. And that's the thing that I like the most about Bayesian statistics, is that's what Bayesians do. So if I were trying to understand what is the distribution maybe of the mean in a normal distribution and I didn't know what the covariance matrix is, I would integrate over that thing and you get a t-distribution at the end of the day. But I have a distribution on vectors that's averaged over the covariance matrix, which is a little bit different from just taking the covariance matrix and just plugging it in your best estimate for everything. So I'm a big fan of averaging over uncertainty. That gives you better predictions. So that's the name of the game. How do you break space and how do you average right? That's what statisticians do. And by averaging, we reduce variability. So and that's why Bayesians have become popular in the last few years, is that they're averagers. They get better predictions. Our intervals tend to be a little bit wider because of that some people don't like, because you're averaging over effects and you're not pretending like you're certain about things. But that also makes it so you're not surprised when you're actually forecasting. So I'll just leave those as just generic points. Let's run through a conjugate analysis just real quickly. And you're doing something like this on your homework. So, conjugate analysis. For sigma inverse, so where xi's are going to come from a normal distribution with mean mu and covariance sigma inverse. So this is a k by k, this is a k by 1, and this is a k by 1. So multivariate normal stuff. So I'll just write down what the likelihood looks like of everything. I'm going to say, let's just make this simple. I'm going to say this is known. So we'll do this analysis. I'll build up my likelihood function on sigma inverse. And I'm going to condition on all of my data, where my data is just all of my vectors. So instead of those being scalars, those are all just random vectors. And I'll condition on mu. So this thing is just product I goes from 1 to n, sigma inverse 1/2 e to the minus 1/2 xi minus mu transpose sigma inverse xi minus mu. So that's just a multivariate normal. And I dropped the 2 pi stuff because it doesn't really help out. You'll notice that I drug this -1 inside right here. I can go either direction on this. Those are both true. So I like it there so that I can read off this parameter sigma inverse, sigma inverse. In the homework problem, it's the opposite of this. You're thinking about sigma and not sigma inverse. And I just do that to create the confusion so that you can work through it once. So if somebody's working on that other scale, you know what they're talking about. I personally like sigma inverse more than covariances, but I understand they're the same things in some sense. So there's this interesting conversation that we were having last time. Sam had brought it up. I think a precision element is like the inverse of the covariances or something like that, but just think about what you did in linear algebra when you inverted a matrix. You're not just taking all the elements and inverting them. A diagonal matrix, you can do that. But that's the only case. So it's this huge linear combination of everything. And so what do those terms represent? The sigma inverse represents conditional independencies. And so I like to understand how different data is related to each other. So it's really a question in this vector right here. How is this element related to this element? So maybe the ith element and the jth element right here, and I want to know how they're related to each other. In the precision matrix, if the ij entry is a 0, it's telling you that they're conditionally independent, where you're conditioning on everything else in the set. So given everything else, those don't have any relationship. It doesn't mean that they don't have any relationship. It's different between them just having no relationship to each other, and given everything else, they have no relationship. So in the presence of other things, I don't really need to model that relationship because the other things are supplying the dependency. It's exactly the same thing in regression. So if you understand how regression works and that everything else held constant thing, and how ridiculous that actually is in reality. So it doesn't actually happen, I don't think, but it's maybe a useful tool nonetheless. So I'll say very often people do this sort of analysis and just try to understand what the distribution is on there, estimate zeros. They'll do that in finance to understand which stocks covary together. Maybe they don't have any relationship to each other given the entire market. So you could use that strategy if you're designing a portfolio. That if this stock goes up or down, it doesn't affect this other one. So possibly you're really risky and you like all your stocks to go up or down together. That's a strategy. So either you get really rich or you go really broke. And some people are a little bit more moderate in their gambling procedures. So it is all gambling at the end of the day. People also do it in genomics. This sort of thing, it's very popular where you're trying to understand the relationship maybe between different genes. So if they covary together. They don't actually look at the genes explicitly, instead they might look at something like microarray data, where they look at phenotypic traits or something that are proxies for genes. So they'll take their phenotypic traits, microarrays, throw them into a vector. Basically, they're just resolutions of like green or red spots. So things that highlight up. What they do is they take an organism, they throw it into a blender, they blend it up, they pour it over this plate, and the plate is designed so that there's these little spots on the plate that highlight a certain color if a certain gene is present. And all the little spots on the chip represent different groups of genes. So maybe they're SNPs, maybe they're something that has to do with a phenotypic trait like your hair color or your eye color or something like that. And they look to see which one of these covary together. You might build a regression model and try to understand which groups of genes are responsible for different traits or different diseases or different propensities for getting different diseases. So that's all of statistical genetics. So very powerful tool in there for doing that sort of analysis. This is at least the foundation for doing analyses like that. So I think there's a lot to be said about precision matrices, and I've given you a mini handout so you can read about the interpretation of everything online. Okay, so here's our likelihood function. Now we just need a prior distribution on this thing. I'm going to rewrite this just real quickly. So let me just rewrite this thing right over here. So this is going to look like sigma inverse to the n over 2, and then e to the minus 1/2 trace. I'll just drop right in there. Sum, I goes from 1 to n, xi minus mu. Give myself some room. Transpose sigma inverse xi minus mu. And again, the reason I can just drop a trace in there is that this is a 1 by 1. It's just a scalar, so the trace of the scalar is that scalar, so I haven't done anything bizarre. Let's give myself just a little bit more room. So that's the likelihood function. Now we need to multiply this by the prior. So and the prior is going to be of this form, and I'm going to use this distribution, but I'm going to place it over sigma inverse. And we'll use the rest of the same notation, but we'll swap out V for our precision matrix. So our posterior distribution, given all of the data and mu, is going to be proportional to this thing, sigma inverse n over 2, e to the minus 1/2 trace, and I'll do a little bit of rearrangement on here. So on the homework, I asked you to show that cyclic permutations over traces were equivalent to each other And so if you don't know that, I'm just going to state it as a fact. But I think any elementary linear algebra book has this in there. So this is going to look like this. So I'm going to take this thing, I'm going to take this sum, drag it out for a second, if you want to think about the steps, and then I'm just going to permute these things around. So I'm going to permute that over here, and then I'm going to pull that one over. And then I'm going to vary in the sum again. So this is going to look like xi minus mu, xi minus mu transpose. I'm going to just be clear as to where that sum ends, and this is times sigma inverse. So again, that's just the cyclic permutation thing. All I've done is pulled the sum out, spun those things around, rewrote the inner product by spinning it around as the outer product, and I've got something that looks exceedingly Wishart in terms of sigma inverse. So you can already see that sigma inverse is the conjugate prior. So I'll multiply in by the prior to get the posterior. So this is the likelihood, and this is the prior. So we'll just follow our notation. I'm going to forget about the whole normalizing constant thing. If I were integrating over the Wishart, then I would need to remember one term in the normalizing constant, and it's this one. So all that stuff I could just forget about. I've never needed to know that in my life. So I've never even worked with a multi-dimensional gamma function because I'm a Bayesian and all my normalizing constants don't mean that much to me, and I just toss them. So this is going to look like e to the minus 1/2 trace omega inverse sigma inverse. I've already messed this up. I need the leading term right there. So this is sigma inverse absolute value and determinant gamma minus k minus 1 divided by 2. So just like in the gamma distribution, I never absorb that and try to simplify it because I need it there to recognize what the parameters in the Wishart are. So this thing can be simplified. Sigma inverse, and I'll just combine terms. This is n plus gamma minus k minus 1 over 2. So I'll just circle those. Those are the things that I need to recognize to identify this Wishart. This is e to the minus 1/2 trace. This is going to be the sum of the xi's minus mu, xi minus mu transpose, plus omega inverse times sigma inverse. I guess that looks good. That looks good enough for me. So that's the thing. So where do I recognize everything? I recognize this thing. That's I goes from 1 to n. So that's the other parameter right there. Keep in mind in the notation, this is the confusing part, is that's an omega there. What I wrote down over here is that's omega inverse. So the inverse of this is the new updated omega parameter. So this thing is a Wishart with parameters n plus gamma and sum of the xi's minus mu, xi's minus mu, transpose plus omega inverse, all inverted. There we go. So just like we've been doing all semester, we just recognize the form.
Is it usually useful to convert that sum of xi minus mu stuff into in terms of x bar? And
maybe. So if you were integrating over mu and integrating out mu, like I think is maybe a problem on the homework, then you would be inserting the x bars. So the analysis I did, I gave you mu. But usually in a real analysis, I wouldn't give you mu, and this would end up changing the problem a little bit if you integrated over mu. So you turn everything into, it would still be a Wishart distribution, but it would be a different Wishart distribution. If you integrated both mu and sigma inverse out and you did the predictive analysis, you get a multivariate t. So, and that would involve the x bar. And the homework problem involves the x bar. But I would say for this problem, there's no x bar because we know mu. It's a bit of a fiction. But if you're coding up a Gibbs sampler, this is exactly what you would do. So what is the expectation of this thing? We end up just looking at that right there. So our expectation for this analysis, sigma inverse, and I'll write it like this given everything else, it's just x and mu. Maybe it's worth writing in here. So usually the hand of the statistical god won't come down and say, here's the mean vector, you get to know it. So in some cases, we kind of pretend that we know it. And what we do first is we center our data. So we center the data, subtract off the mean, and then have everything stick, centered at 0. And then we just model the covariances. This is what people do in Gaussian processes. So it's very similar to this sort of analysis, but a Gaussian process is a parametric version of a covariance. You're not estimating all the elements individually, but you're estimating functions that are spatially related to each other. So it's a parametric form of a covariance. But if you understand this analysis, you can march right over to a Gaussian process instantly. So I'd say this is the foundations for that. So this thing is just n plus gamma times this. Sum of the xi's minus mu, xi's minus mu, transpose, plus omega inverse. And this whole thing is inverted. So question, what might you pick gamma and omega to be? So same conversation we've been having all semester, really. Get rid of this. I usually stare at these sort of things and I think, what would make sense in terms of the expectation if the expectation was sensible? And I think in this case, maybe the expectation is sensible because it's not a multimodal distribution or anything like that. So the expectation does have some sense to us. So I've got just a question. The question, what gamma and omega inverse? Let me just appeal to our non-Bayesian friends. What is the answer that they normally give you for this sort of analysis? If I gave you mu, what do you think the MLE of the model is? So if I took the likelihood and I just maximized it. So question 2, what's the MLE? Let me just do it this way. MLE for sigma. So the covariance, I put it on the other scale. This might not make sense to everybody that hasn't had a full-blown inference class, and if you want to connect the dots on this rationale, take an inference class. The full-blown deal, and you'll know more about non-Bayesian statistics as well. It's the what?
Oh, we know mu actually is not.
Yeah, it's not, we know mu. So what do you think the MLE for this is? That just means that I take this thing, the maximum, over sigma of the likelihood function for sigma given x in mu. It's a calculus problem. I'm not going to ask you to do it. There is an answer to it. Most people know what this answer is, but they might not have derived it.
Wouldn't it just be average square deviations from the mean?
Yeah, I think so. So it's this. Sum I goes from 1 to n, xi's minus mu, xi minus mu, transpose over n. So that's the MLE. If you want to know the unbiased estimator for everything, you replace those with x bar and you divide by n minus k. But since we know what mu is, this is the unbiased estimator when you know what mu is.
Have we, at this point, gone into more detail as to what the significance of the unbiased estimator versus the biased estimator is?
The significance is whether or not you like being biased or not. Personally, I do. So, I love bias.
But I suppose I would be more from the definition of bias.
We do more of it in inference class, and we spend a lot of time harping on that. So, and study these properties of estimators. I can't do both in this class, so I have to do some sensible partition, just so we can get through all the Bayes. So what is the thing with unbiased estimators? Probably nothing if it means you have a trade-off in higher variability. And so we've all heard about bias variance trade-offs. So very often when you bias things a little bit, not an extreme amount, but you give some traction to the problem, you kind of bias things and steer it in a direction, you can reduce the variability. So I think that's just a claim that we'll just stick with since we've heard it. But I think biasness on its own, and you just tell me something is unbiased, I don't care. So I need to know more. So any which way you cut it, this isn't a bad estimator. So it also has good properties. It's consistent, it converges to the truth, and in some sense, in some loss function, it's optimal. And so we'd have to look at that loss function. We're not quite there in the class, but here's just some facts. So if I wanted to match this answer to that answer, what would be the equivalent sort of thing? So maybe we could use this rationale to answer maybe what those should be. Yeah, some sort of like, what does this mean? 0, I can deal with that. What the heck is this? That's not positive definite, some 0 matrix. But I can think about these funky concepts because now I'm used to improper priors. And you would induce an improper version of this. And that's what I handed you on the homework, was an improper version. So the improper prior that I gave you on the homework is the Jeffreys prior. And now we're at least comfortable with those concepts because we've seen those work out well in our favor before. So with gammas, with normal distributions, with infinite variance and things like that. Keep in mind the Bayesian does not do inference off of the prior. They use it as a tool to build a posterior with certain properties. So if we were thinking of this as some sort of knobs on it and I wanted certain properties, I could take a Bayesian analysis, match what my non-Bayesian friends are thinking if I really liked all of those properties, so I would get those out of the expectation, but I'd also get the best thing about the Bayesian analysis, that I'm also getting a probability distribution over everything. So it gives me the ability to average over a spectrum of sensible answers. So yeah, this would be akin to that. So it turns out MLEs are transform invariant. We've looked at that before. So that means I would just invert this thing, because this is on the invert scale, and it would be just like this if that was 0 and this was the 0 matrix. And so that might be choices that you might make. So, and in some sense, they're non-informative. So if you like that language, I hate it. So, but some people will enjoy it, because then they don't have to talk anymore about it. So you might say it's transform invariant. So in that sense, it's non-informative. So on every transformation of the problem, I'm supplying equal information with the Jeffreys prior. So in that sense, it's non-informative. So I'm not supplying information in a way that I want the data to exclusively drive the information in the analysis. Okay, let's switch gears. So let's go to hypothesis testing. So I'll just give you a mini prelude to this, and we're going to spend the next couple weeks on this. So I'll give you a new homework. The new homework is already posted. We'll have to extend that homework date, so it won't be due next week. It'll be due after the break. And depending on how far we get next week on this stuff, we'll come up with a tentative due date. Okay, hypothesis testing. assume that you guys know everything about this stuff in classical land, and I don't need to tell you anything about it. So I'm going to collect some data real quick. Probably the p-value is really low on that, so I'm going to reject. Does that make sense to you, what I just said? If it does, you know a little bit about hypothesis testing, at least the classical rationale of it. So let's just see what you know. So I'm just going to ask you some questions about this so I can figure out what do I need to cover. So what are typical hypothesis testing tools? Let me just make a statement. The idea is something like this in statistical land. So very often we'll do something like this where we'll talk about our null hypothesis. I cringe when I just hear these words right here. But it's okay. I mean, people do talk in this, so I'm allowed to cringe. So I might say theta is an element of some set. So for instance, example, maybe theta is greater than theta naught. So this is one example. So I might have a competing hypothesis. So this is usually called the alternative. And this might be that theta is an element of another set. And it might make sense to make this the complementary set. So I might say, for instance, theta is less than theta naught. So example. There's lots of different versions of this. I could test if theta is in an interval. I could ask questions, is it in the interval or is it out of the interval? That's a possible question. This is the one-sided hypothesis. There's other types of questions that we might ask. So, other hypotheses. This might be theta naught is theta is an element of theta 1 to theta 2. So that's some interval test versus theta is not an element of this set. So basically, I got some interval here, theta 1, theta 2, and I'm asking, is theta in here? Versus, is it everywhere else? That's the interval test. So, and then we've got the test that gives everybody huge headaches. Theta is equal to theta naught versus theta is not equal to theta naught. I'm going to say this. This is the most common test performed in all of the universe. I only know about our planet, so I assume that we're the only ones doing this nonsense. So this couldn't occur twice in the universe. This is a crazy question. So if theta was a continuum, this almost doesn't even make sense to me, and I'm going to just point that out as a fact, and we'll talk about that. And this is really where a Bayesian and a non-Bayesian really get into arguments.
It's going to become a naive question, but like, what's the difference between the two? Because when we actually do a two-sided, it's kind of like the interval, because we're saying, oh, is it more than this margin of error from
kind of, yeah.
So what's the difference between it?
I'll tell you next week. And I'll do you even a better solid. There's a paper online that discusses the interval test and the point test. And it's called, what Bayes factors are, sorry. The paper is called What P-Values Are and What They Are Not. It's something just like that. Mark Jervis wrote the paper from Carnegie Mellon. I'd encourage you to have a look at that paper. I'll be going over it next week, and I'll distinguish these three tests for you. Josiah makes a good point that in some sense, the interval test subsumes all of these other tests. So if I take the limit and I collapse those into each other, that's the point test. So in some sense. And if I took this and I blew it out to infinity, or that off to negative infinity, I would get the two one-sided tests out of it. So I will demonstrate to you one of the foibles of p-values. So where p-values really come apart, and I'll talk about the non-coherency of p-values. And you can really see it in this example. So I'm going to point out and make a global statement that you've probably never seen this test. What the uniformly most powerful likelihood ratio test is, computing a p-value for that test, and the reason why is it's an embarrassment. So to Neyman and Pearson. So they don't even talk about it. And I'm going to highlight it in this class just for the fun of it. So, and I'm going to tell you that Bayesians on the interval test do something that I think is exceedingly sensible. I think one thing that's kind of nice is that Bayesians and non-Bayesians often agree on these one-sided tests. There's absolutely no agreement here between Bayesians and non-Bayesians. And I think the Bayesian makes a lot of sense here in the non-Bayesian. The Neyman-Pearsonian doesn't make any sense on this test. I really don't like it, but I'll tell you what it means, and I don't think Neyman and Pearson is wrong. I just think it just highlights our misinterpretation really well as to what a p-value is. So a p-value is not a measure of the hypothesis. So you have to come up with alpha. If p ducks alpha, and you pick alpha up front, you're controlling error rates, which is an entirely different thing of building a measure of support for the hypothesis. So these are the things I will untangle, and I'll tell you where the argument is. I'm going to point out, when I see people do these sort of tests in sensible ways, and it's a real question and it makes sense that that is the answer to a real question, and they do everything using design of experiments, I don't have any problem with what frequentists do. But the point test, whenever I see it, I just shudder, because I think that it's highly misinterpreted. We'll be going through those differences. I just want to point out, here's what some people like to think about. They like to think about the error rates of everything. So usually non-Bayesians dwell on this. And this is probably what your Stat 101 teachers were dwelling on, but maybe not telling you all the dirty little secrets as well. We know that they're there. So we're going to try to untangle those. So there's the truth. And then there's our guess at the truth. So what we believe the truth is. So the truth could either be H naught or the alternative. And I could guess either H naught or I could guess the alternative. So I like to always say there's two types of errors out there. To any decision you ever make, there's two types of errors. And I do like the idea of controlling errors. So in some way I am a Neyman-Pearsonian when I think about social problems. Which kind of error are we going to compartmentalize and control and try to minimize? So I like to have control over that. So Neyman-Pearson don't give you control over that so much. So right here, this is no error. Here is an error. Right here, the truth is H naught, and I guess H1 instead. This is an error right here, and there's no error here. We like to distinguish these different types of errors because in some sense they're different. So, and these are the problems that you should think about anytime you're making an error, is what are the two potential errors? There's at least two of them, and think about which one you value the most. So, like in a court of law, something like that. There's this notion that criminalizing an innocent person is a more egregious act than letting a criminal go free. And you'll hear debate on that. And I kind of believe that, you know? And so that's the presumption of innocence criterion. Is it actually true? Unfortunately, probably not. It depends on where you are and when you're there. So, what are the names of these errors? What's the type 1 and what's the type 2? Is this the type 1 error? This is, yes. So the type 1 is when the null is true and you reject it. So this is rejecting the null hypothesis. That's a type of error. I am not going to have the conversation about accepting errors versus rejecting errors. I consider it all the same stuff. I understand Popper. I understand the philosophy behind all this, and I just don't want to get into it.
So I just wanted to point out, I think in engineering this is akin to what people would call probability false alarm.
Yeah.
Misdetector.
That's it. Yeah.
It's just the same thing.
Same thing. And there's also precision and recall if you're a computer scientist. And if you told me what the sample size was, you told me the type 1 error and the type 2 error, I could give you the precision and recall. I could compute those for you. It's a little bit different of a thing in classification. It's a different formality for talking about errors. But yeah, false alarm rates are exactly these type 1 and type 2 errors. There's also sensitivity and specificity. And so you'll want to get all these different notions down. So if you're ever talking to different people, you just calibrate over. So I usually don't talk about type 1 and type 2 when I'm talking to my computer scientist friends. I usually talk about precision and recall. We're going to stick to type 1 and type 2. In this class, they're not exactly the same as the other stuff floating around out there. But in some sense, they're equivalent. So I will point out in classical land, usually what they do is they fix this error rate. So this is usually, in classical land, it's common to fix this. This is called the alpha level. So that's usually like a pre-specified number that people arbitrarily pick, and very commonly people will use multiples of 0.05. And that has everything to do with, I love to torture myself and think about what would happen in the world if we had 6 fingers. So, and we counted in base 12 and not in base 10, how many rounding decisions we would make arbitrarily different and what would the universe look like. So I don't know how much of a difference it would make, but I know it would be different. So oftentimes they fix this, and in the classical framework, they try to minimize that. This is the name and Pearsonian framework, and I'm going to tell you a little bit about it, but we're not going to dwell on it too much. We'll do some calculations. I'll assume things that you know, and then you'll correct me, and we'll clear this up in a review session or embed another lecture if we need to. But this is the whole p-value thing. If p-value dumps alpha, if the model is correct, that's a big assumption. So if the model is absolutely correct, and you fix alpha up front, and you collect data out of that process, and if the p-value that you compute dumps alpha, then your type 1 error rate is controlled at alpha. And if you compute a p-value in the right way, and I'll tell you how to do that, or at least the correct way, you can minimize the type 2 error. So let me give you a example. Some scientist walks into my office and says, I have a hypothesis. Some of you have already heard this before. I've got a theta naught, and I've also collected a whole bunch of data. I could say to them, what would you like the type 1 error to be? I.e., if the null was true and we reject it, let's control that. And they might say, I want it to be 0.07, because that's the standard in my field, 0.07. And I say, okay, cool. So this is a procedure I could do. I could fix the type 1 error rate at 0.07, and I could generate a uniform random number. So this is my device. And the scientist says, would you like to hear the null hypothesis? And I say, no, I don't want to hear it. Just keep it. And would you like to look at my data? No, I don't want to look at it. I generate a uniform random number, and if that number is less than 0.07, I say reject your null hypothesis. So I don't need to look at your data, I don't even need to know what it is. But that system of just generating an arbitrary uniform number and seeing if it dumps 0.07, it turns out has a type 1 error of 0.07. It could have been right, it could have been wrong. I put some probability 0.07, I generated with something probability 0.07, and I have a type 1 error of 0.07. And it turns out it's true. And we will study that claim a little bit later if you don't believe me. Here's the trade-off. The type 2 error rate by doing that is tremendously high. Does anybody know what it is? It is. Go ahead and say it.
0.9.
It's 0.93. It's the complement. So I have a huge type 2 error rate. The p-value thing, if it's done correctly, would preserve the type 1 error rate at 0.07 if I use that for my alpha level, but doing this thing Neyman Pearson came up with minimizes the type 2 error rate, and it would be much, much smaller than my 0.93. So I think people don't spend enough time talking about type 2 errors. It probably is the important thing in the Neyman-Pearsonian framework. And Bayesians have a totally different framework for working through hypotheses. In some cases, their framework corresponds to the Neyman-Pearsonian, and in some cases, they don't have any overlap, and there's total disagreement. And the total disagreement happens on that point test. It always happens. We don't agree with each other at all. And I'll tell you where the argument arises. And you can decide in your life which paradigm you want to adopt. The paradigm I try to adopt is not doing hypothesis testing unnecessarily. So I don't take that as the, well, P was small. You know, there's the end of my analysis. I try to do estimation and understand what's going on in the process. I have done hypothesis testing. So in some cases, it really is the question. And I'm always concerned about it if I've done it correctly, if it really is meaningful, or if I just came up with a number for somebody that made them happy. We'll talk about all of that next week. So let's buckle up for hypothesis testing. Have a look at the new homework. Please read through that paper on what p-values are and what they are not. And I will be covering the paper early next week. Yeah. Thanks, y'all. Have a great weekend.